Welcome to Tiny Show and Tell Us, the bonus series where you write in with your favorite science news or factoid, we read your email aloud, and then we dive deeper. I'm Sam Jones, and I am here with my co-host, Deboki Chakravarti.
Hi, Sam. Last time we went Team Wasp, for the moment, at least, because they're great for biocontrol for pests. And then we also talked about the importance of iron and hemoglobin. And also a reminder for all of you that if you have a story you'd like for us to cover on Tiny Show and Tell Us, all you have to do is write us an email. So you can email us at tinymatters@acs.org or fill out the form linked in the episode description.
Cool. Deboki, you want to go first this time?
I sure will. And I've got two for you because they're both kind of short, but they're also very fun.
Ooh.
So I'm going to just tell you them both right off the top. The first is from listener Mary, who wrote, glass is technically a liquid.
Okay.
And the second is from listener Zoe, who wrote, milk is fluorescent due primarily to riboflavin.
All right.
So let's start with Mary and whether or not glass is technically a liquid, because it turns out it's not. But it's also not a solid really fully. It's something in between called an amorphous solid.
Whoa. I feel like I should have known that, but I didn't. So I'm so glad Mary wrote in, and it was like, Mary was half right.
Yeah, exactly.
But it's so confusing.
Right. And so one of the reasons that people sometimes think that glass is a liquid is because they might go to old cathedrals and you'll look at these window panes and sometimes they'll be thicker at the bottom. So it looks like they've kind of melted. And yeah, I hadn't heard about this until I think this past year. I think we actually had a SciShow Tangents that was about glass, and someone wrote in asking about this phenomenon. And so, yeah, apparently it's something that people notice, and I think it totally makes sense. You'd be like, oh, that makes sense that glass might be this liquid, and it's over time kind of melted downward and created this thicker window bottom. So why is glass not a liquid, though? So solids have like an organized structure to them, right? Especially something like crystals. Those are super organized. The atoms inside are laid out like very, very structure repeated kind of things. Liquids don't have that. And glass also doesn't have that super organized of a structure. So when you are making glass, you will melt it into a liquid. But when it cools down below its melting point, it doesn't solidify it. It becomes what's called a supercooled liquid. But then as it cools down more, it gets below what's called the glass transition temperature. And this is where the atoms in glass stop moving. And so at that point, it's not super organized like a crystal, but it's also still more ordered than a liquid.
Okay.
And amorphous solids can flow, but they can flow super slowly. And eventually, I think we're probably talking on very long time scales, they might get into more of that crystallish kind of order within them, in terms of those atoms and how they're arranged. This still doesn't actually explain why you might see these windows that have these thick bottoms to them, because the temperature that those windows are at is still way below that glass transition temperature. So the article that I was reading from Scientific American on why glass windows might do this says that it might be more actually due to how those windows are made rather than them being liquidy. So yeah.
That is so interesting.
Yep. Categorizations are weird.
Yeah. Amorphous solid, you said.
Yes. Amorphous solid.
Okay.
When you see glass, that's what you're looking at.
Okay.
Let's get into fluorescent milk. This was also really cool. So just as a reminder, Zoe wrote, milk is fluorescent due primarily to riboflavin. Riboflavin is vitamin B12. It's in a lot of things like meat, green veggies, and yes, it's also in milk. We need it for our skin, for the lining of our digestive tract. It's, it's a thing that our body uses, and it's also fluorescent. So for a quick reminder on what fluorescence is, this is what happens when certain chemicals that are out there, you shoot a light at them with one wavelength, and they'll actually emit light at another wavelength. So with riboflavin, you can shoot a light that has a wavelength of 349 nanometers at it, which is in the ultraviolet range. And the riboflavin will then emit light at 532 nanometers, which is green. So yes, milk can actually glow this greenish yellow color when it's irradiated with ultraviolet light.
I guess I've just never looked at milk under UV light.
Right. Yeah. I've never thought that seems like something I want to do.
Yeah.
But there are actually really good reasons to do it. That's what I found really fascinating when I looked into this. Riboflavin is not the only molecule that can fluoresce in milk. And what scientists have realized is that they can actually use fluorescence spectroscopy to test the quality of dairy products. And it's a great technique because it's fast, it's sensitive, and you don't have to destroy any of the milk to do it. You can just shine a light at it and see, is it fluorescing? So one really, really interesting application is like if you want to know if your milk is from grass-fed cows, you can use fluorescent spectroscopy because when cows are grass-fed, as opposed to like cows that are eating grain, they'll actually have chlorophyll that'll show up in their milk because that's like one of the byproducts of them metabolizing the grass. And chlorophyll also fluoresces, so you can use spectroscopy to figure out how much chlorophyll is in the milk. And that's just one example. There were a lot of other ways that I found, like you can use fluorescence to like figure out where the milk is from geographically. Like there's just all of these different applications for figuring out the quality of milk from how it fluoresces.
That is so interesting. I had no idea. And of course, it's not just when you're trying to figure out, like, is it chlorophyll? Is it something else? It's not just like shining a UV light or something, right?
Yeah.
Like it takes a lot more, but you could still, in a chemistry lab, you could find out a lot about that milk.
Yeah.
Oh, so cool.
Yep.
I love that. All right. Well, my tiny show and tell us is from listener Joshua, and it is a very in-depth one, very well explained. So I'm going to stop at a couple points, but mostly just go through what he's sharing.
Okay.
So Joshua wrote in saying, today I would like to share a not so tiny matter, which would be well worth telling your audience about. Multiple exclamation points. For my master's research, I worked for NASA Goddard Space Flight Center, modeling the very fascinating topic of the gravitational waves emitted from a special black hole binary called extreme mass ratio inspirals. That's EMRIs.
Oh.
Yes. So let's talk about this. Continuing with Joshua's email. At the center of every galaxy, we believe there exists a very massive black hole, which can be millions to billions of times the mass of our sun. Around these massive black holes, we could find a group of stars which could contain a much smaller black hole with a mass comparable to the sun. If this group of stars falls toward the massive black hole, then the stars would likely be torn apart by the force of gravity and contribute to the swirling vortex of hot plasma called the accretion disk. By the way, Joshua, I think you did a really good job of explaining this.
Yeah.
Okay.
This is very vivid.
It's very vivid. And then Joshua writes, however, that much smaller black hole, if the conditions are just right, will not be torn apart. Instead, this smaller black hole will slowly fall into the massive black hole, kind of like a marble slowly spiraling down a well, which, great visual.
Joshua, I have a question. How do you go about your daily life, like, knowing this? Like, this is, like, something that you think about all the time, and then also you go buy groceries.
I know.
Are you thinking about how somewhere out there is a tiny black hole sinking into
a larger one?
Yeah. Like, I just feel like that would just be... I would not be able to think about anything else.
Yeah. No, it's wild. Okay, so Joshua has that marble slowly spiraling down a well visual.
Right.
And then writes, due to the very stark differences in these two black holes' masses, we call this system an extreme mass ratio inspiral. So that's what that is.
Okay.
All right. Joshua continues. As the marble falls down the well, it creates wiggles and wobbles in the fabric of space-time that we characterize in the scientific community as gravitational waves. Love that. Encoded within these signals is rich information which can aid us in addressing many unanswered questions within the field of astrophysics that we hope to answer. The future of gravity wave detection will be made with the Laser Interferometer Space Antenna, or LISA, which is set to launch in the mid-2030s. This detector can be described as a series of 3 satellites projecting laser beams in an equilateral triangle so big that you can inscribe the sun inside of it. This triangular satellite constellation will cartwheel in a coalescent orbit which trails the Earth around the sun. Okay.
Sorry, I just want to like make sure I'm picturing this right. So there's going to be these satellites and they are following us as we go around the sun, but they're also really, really big. Like it's like bigger than the sun too.
Yeah. So before I get into the last bit of what Joshua sent, I'm going to just talk a little bit about LISA.
Okay.
The Laser Interferometer Space Antenna, because it's also very new to me.
Yeah.
So like Joshua said, LISA is a space probe. It's going to detect and measure gravitational waves, which are sometimes referred to as ripples in the fabric of space-time, which is just like the best visual
right.
ever. So what's cool about LISA is that it will be the first space-based gravitational wave observatory.
That we know of.
Yeah, right. Okay, so LISA is made up of 3 spacecrafts that are separated by millions of miles, trailing many millions of miles behind Earth as we orbit the sun. So according to NASA, I'm quoting NASA because I think this is a really good explanation. And this is
the same way that we're quoting Joshua. You guys are, you know how to explain this stuff.
Yeah, exactly. So according to NASA, quote, these 3 spacecraft relay laser beams back and forth between the different spacecraft, and the signals are combined to search for gravitational wave signatures that come from distortions of spacetime. We need a giant detector the size of the sun to catch gravitational waves from orbiting black holes that are millions of times more massive than our sun. Why do they need it to be so big? This is me now. The quote's done. So, why do they need it to be quite so big? I don't know for sure. But I assume that, you would need a very large amount of area that's covered to really be able to detect something like a gravitational wave.
Yeah.
And this is in partnership, I'll say, with the European Space Agency, and it's scheduled to launch in the mid-2030s, which Joshua mentioned.
Yeah, I wonder if, when I'm thinking of a gravitational wave, I'm picturing it like an actual wave in an ocean. And so I wonder if it's sort of like if you don't capture a large enough area, you're just not going to see as much of the wave to make it look like a wave. Like if you zoom in too close on a wave,
you have no idea what it is.
It's just going to look like an even terrain.
It's just water.
Yeah.
Yeah, totally. I think that's definitely a part of it. And also, I'm going to link to a great little video that's on loop from NASA, because I think that will help people visualize what the heck is going on here with LISA.
I'm going to take a quick look. Oh, wow. It's just going.
Mm-hmm.
I like this animation because it makes it look so, not simple, but it feels so straightforward, but it's there's so much
that's happening.
Yeah.
Yeah.
How precise does it need to be? I have so many questions.
I think quite.
Yeah. And it has to be an equilateral triangle. Is that really important?
Yeah, it seems like it.
Oh, man.
Yeah. So this is just a little looping video that I'll link to where you have this big LISA detector trailing behind Earth as Earth is going around the sun.
Yep.
And hopefully picking up on gravitational waves.
Yeah.
Okay, so going back to Joshua, last thing that Joshua wrote, before LISA comes online, we need to model these gravity wave signals using theoretical models, mathematical techniques to find solutions to these equations, and computers to crunch the numbers. My master's research focused on building gravitational wave signals for EMRIs, now considering the effects of a massive black hole that spins.
Ugh.
The road ahead for understanding the elusive nature of black holes, among many other adjacent fields, is incredibly exciting with the prospect of gravity wave observations with LISA. Stay tuned! !
We sure will.
We will. But yeah, thank you so much, Joshua. This was great. I was as I was reading it, I had to keep stopping every sentence to just visualize what was going on. But you did a great job of using just some excellent examples and very descriptive language that helped it make more sense.
Right. Yeah, I think, like I said, it's just wild to me that we can think about the universe in this way and that people do that and then go live their normal lives knowing this about the universe.
I know. It is wild.
Yeah. Well, thanks to Mary, Zoe, and Joshua for submitting to Tiny Show and Tell Us, a bonus episode from Tiny Matters, created by the American Chemical Society and produced by Multitude.
You can send us an email to be featured in a future Tiny Show and Tell Us episode at tinymatters@acs.org, or you can fill out the form that's linked in the episode description. We'll see you next time.